Hi class, we're going to cover 5.1 today, which is all about exponential growth, something that's very applicable in the world today as we're worried about exponential growth with the cases of coronavirus at this point. Okay, so this will kind of teach you why we're trying to flatten that curve and teach you about what that curve actually is. So exponential growth today. So one other thing that we see, actually there's several things that we see in real life that have exponential growth. And one example here is the growth of bacteria. So here are some data points showing that every 20 minutes, so each 20-minute period, we're seeing the number of bacteria go from 100 to 200, so it's growing by 100, then from 200 to 400, so then it grows by 200, then it grows by 400. So what's happening, and we can visualize exponential growth as we plot each one of those points. So we see it growing kind of slowly at the beginning, and then eventually that growth grows faster and faster. Those slopes get steeper, the rate of change gets faster, and we see that exponential growth. So this is an exponential curve right here, where it goes from slow growth originally to very fast growth here at the end. Okay, and exponential growth will typically continue this way, which is why we worry about exponential growth sometimes and want to understand it, because when something is growing that fast, often if it's populations, we'll run out of resources. If it's things like we're seeing today, if it's a virus, then we're running out of our normal capacity in hospitals and things like that. Okay, so we want to understand exactly how this exponential growth is happening. What is creating this exponential growth? And we're going to put equations to that today. So I just want to go back to those data points. I've kind of listed them out here, and we're going to look for that pattern in this data. What is causing that exponential growth? So for each 20-minute period, just like we did with linear equations, I want to relate everything back to this original amount. We started with 100 bacteria. And how did it grow from there? So the first point we look at here goes from 100 to 200. So we can think about adding in another 100, but we can see that that addition is not going to stay constant like it does for linear functions. We would add 100 here, but then we're going to add 200 here and add 400 here. So that won't be constant addition, which creates linear functions. So instead, what we're going to look for with exponential functions is we have exponential growth when we're constantly multiplying by the same thing. So here, as we go from 100 to 200, we take 100 times 2 to get to 200. So we want to look at that pattern there. So the first data point, 200, equals that initial amount, times 2, and we will get to the 200 we see for an input of 1. Then for 400, we want to relate back. We can see it's 200 times 2 again, and we'll continue that pattern of times 2, but we want to relate this back to the 100. So what I'm going to do here is say, okay, well, it's 200 times 2, and 200 was 100 times 2. That's 200 right there, and we need to take that times 2 again. So really, we're thinking about taking that initial value times 2 twice. And we see an exponent start to come into play here. And as we move on to 800, we see, okay, that's 400 times 2. Remember, 400's right here. That's 100 times 2 squared, and we need to take that times 2 again. Combining those exponents, we see, okay, that's 100 times 2 3 times. And you can start to see that pattern here. This is 800, which I need to take times 2 to get to 1600. So again, I'll take 100 times 2 to the third. I'll take 800 times 2, and that will be my 1600, which I'll think about as the original amount times 2 4 times. And if we continue that pattern, we'll see, okay, to get to the next one, I need to take the previous one times 2 again. That'll be 2 to the 5th. I need to take that one times 2, so times 2 to the 6th to get 6400. The original amount times 2 7 times to get to the 7th time period. And we fill out those last two fairly easily now. 2 to the 8th, it just increases by 1 times 2 with each increase of our input. So then our general formula is where we see that exponential equation come into play, because the exponent is what is changing here. So we see an exponential equation where our variable, the thing that's changing, is going to be in the exponent. So here, if we think, okay, y over here, that was the number of bacteria. And if we think about our x over here, right, that was the number of 20-minute time periods, so number of time periods. Then for each one of these, y, right, so this was 51,200, y equaled every time we took that initial amount, times 2, and that exponent always matched the number of time periods. So we just needed to plug in the number of time periods to know how many times we needed to multiply 100 by 2. And we see right there what an exponential equation looks like. And in fact, that's a really good way. The way we build that is a really good way to build any exponential equation. We have a standard form for exponential growth, just like we had a standard form for linear growth. Our standard form is going to be, we have some number taken times a base to an exponent. And this is where A is called the growth factor. So because our data was doubling with every time period, our growth factor was 2 in this equation. And that's the amount that y gets multiplied, right? That's the amount that 100 got multiplied by with each increase of x. And then C is like the B value in linear equations. It's always that initial value, what we started off with. Okay, so this idea of a growth factor and an initial value creating an exponential equation will help us build exponential equations to match all the different types of scenarios where we see exponential growth. So that's what we want to do next, is look at some more examples. Look at some examples of exponential growth and understand how we can build equations to represent these scenarios. Okay, so here is one. This one's kind of a fun one. We're going to imagine that we have a piece of paper which we can fold in half infinitely many times. Now, it actually turns out that I believe it's only 7 or 8 times that you could fold a piece of paper in half. This physically, you can't fold it in half anymore after that. But we're going to imagine, just for this problem, that we could do it as many times as we wanted to. So we can see how that growth continues over the number of times that we fold this paper. And we're going to use the fact also that a piece of paper, let me zoom out a little bit here so you can see this whole problem. A piece of paper is approximately 0.1 millimeters thick, so very thin, right? 0.1 millimeters is not very much. So we want to use this general form, the y equals c times a to the x. This is going to be exponential growth, and we want to see how. So we want to identify, okay, in this case, what would c and a be as we continue to fold these pieces of paper? So we really need to first identify for ourselves, what would y and x be for this equation? So we're going to fold the paper and the thickness is going to change. So x is going to be the number of folds, where we'll start with just 0 folds, the original piece of paper. And y is going to be how thick the paper is. So thickness, and we're going to start with a thickness in millimeters. So this thickness for our function, if I can write millimeters correctly, is going to be in millimeters. Okay? So think about what's happening here. Then C is the initial thickness. And we know the initial thickness, it's 0.1 millimeters. So then our equation becomes y equals 0.1, because that's what we're going to start off with, a thickness of 0.1 millimeters. And then think about what happens every time we fold the piece of paper. So once I fold the piece of paper once, I'm going to have 2 layers, or that 0.1 times 2. And then I'm going to put 2 layers on top of each other, and I'm going to have 4 layers. So each time I fold the paper, those layers are going to double. So we're going to have 0.1 times 2 to the x. right? Let me kind of rewrite that there. It looks a little messy. I want to make sure we realize that we have 0.1 times 2 to the x, okay? So we have to make sure that we can't take the 0.1 times 2 at this point and simplify the equation, right? Because we always have to do exponents first. So we've got this exponential equation here. And once we have that, now we don't have to do each data point, each fold at a time, saying, okay, after one fold, I have 2 layers. After 2 folds, I have 4 layers, and keep going with that to figure out how much thickness we would have after 10, 20, or 30 folds. We can now just plug those numbers in for x here and figure out what would that thickness be if we could fold the paper 10 times, 20 times, or 30 times. And it's going to be crazy how we see this exponential growth happen here, okay? So we only start off with a thickness of 0.1 millimeters, right? So let's go with, okay, if it's 10 folds, what happens? So after 10 folds, that would mean we have an x value of 10. So we're going to take 0.1 times 2 to the 10th power. And that grows so fast that we're going to get, if you plug that into your calculator, that's going to be about, actually I think it ends up being exact, 102.4 millimeters. Now, we don't often work with millimeters, so I do want to give you an idea of the thickness there. So after just 10 folds of the paper, you know how thick a piece of paper is. That thickness now of the paper folded 10 times is going to be about 4 inches is what 102.4 millimeters converts to. Okay, so we have a 4-inch thick fold now with just 10 folds. That's crazy. Okay, so if we could fold a piece of paper then 20 times, that means we would need a power of 20 here. That's going to be about, already, with just 10 more folds, 104,858 millimeters. And if we think about that in terms of units we know, that's about 115 yards. 115 yards. This one piece of paper that was 0.1 millimeters thick is now standing 115 yards tall. Crazy. And if we go all the way to 30, we know by the image of this exponential growth, right, that this is just going to grow faster and faster. That if we take that 0.1 millimeter times 2, 30 times, our thickness will now be 107,374,182 millimeters, which is about 67 miles. 67 miles tall would be the piece of paper if we could fold it just what seems like not that crazy 30 times. Okay, so that exponential growth grows incredibly fast. Okay, so that's why we always are a little bit concerned about some things growing exponentially fast. All right, so let's do this the other way around. So it's pretty easy to plug this into your calculator. Hopefully you're using that exponent key to plug those in. But if we turn this around, it's a little bit harder to solve the problem. So if we want to instead approximate how many folds, remember the number of folds is y. So now we're trying to, oh, sorry, no, I just said that backwards. The number of folds is x. So we want to know x when the thickness y is 400 millimeters, a little over a foot thick. Okay, then we have a little bit more work to do here because our equation now says, okay, I want to know when y is 400. And so I'm going to figure out what power of 2 I need to take times 0.1 to get to 400. Now, by the end of this class, we will have a way of doing that, but there's a lot of work we have to do to get there to understand what's going to help us solve these exponential equations when we're actually solving for the exponent. Because right now, there's no way for us to get that exponent down. We can't divide off 2 or anything like that because x and 2 are not being multiplied. We have an exponent of x. So we just have to do a little bit of educated guessing here. So let's use some of the information we have up here. We just tested some number of folds. We just tested and saw that 10 folds got us to 102.4 millimeters. And that 20 folds was way higher than the 400 we would like. So we're going to use this information to give us a place to start. So always just test a value for x and give yourself a place to start. So we know that after 10 folds, that we're at about 102.4 millimeters. And we know that this is doubling. So we know that if we go to 11 folds, without even plugging this into our calculator, we know that this quantity will double. And so we will get that that's about 208.8 millimeters. And if we go to 12 folds, we know that that'll just double and get us to about 416, 417-ish millimeters. So we can work off of this knowing how the growth factor works with each increase of x and giving ourselves a place to start. And we figure out here then that it will get to 400 millimeters at around 12 folds, right? We certainly aren't there at 11 folds. We're a little over at 12 folds, but we'd be even greater. We'd be up like close to 800 millimeters after 13 folds. So approximately how many folds? It would be about 12 folds to get us to that 400 millimeter mark. Okay, so we're gonna have to do some guessing and checking if the exponent is what we don't know, at least for right now. Okay, eventually we'll have some new functions, some new tools we can use to solve for that. Right now, I just want you to solve for that, reasoning through what's going on with that, with whatever your growth factor happens to be, and doing some guessing and checking there in your calculator. Okay. And here we didn't even need a calculator once we had a pretty solid place to start. All right, let's do another example of exponential growth. We're going to try and build that equation again by identifying in this situation, what would the growth factor be and what would an initial value possibly be? Okay, so here we've got that an institution promises that investments in their mutual funds are growing exponentially. Okay, so we know that we're working with that equation, we're growing exponentially, so we know we've got y equals c times a to the x. They promise that after 8 years, if $7,000 is invested, our account will be worth $15,000. So time is changing the amount that we have in our account. So we want to also identify that from the very beginning. So x here is going to be the number of years our money is invested, and y is going to be the value of the account. That is changing over time. Okay? Now, we only know that after 8 years, if $7,000 is invested, we expect the account to be worth $15,000. So we know the original investment. We know that C should be 7,000 because that's how much they're asking us to invest. After no years, we'll have $7,000 in the account because we're going to put that in there. But then we're not given a growth factor. We're given that after 8 years, we'll have $15,000 in the account. So we're given another point here. After 8 years, we'll have $15,000 in the account. So what we have to do on this particular problem is actually find that growth factor. We have an x and y, so similar to how we used to find the b value in equations, we're going to find the a value in this equation. Okay, so what we have then is that y is 15,000. That equals c, we know, is 7,000, times a, which is what we're trying to find, and x is 8. Now, we've been doing a lot of work with exponents in chapter 4, so that's going to help us solve this equation, because we can solve this one. The exponent is not what we don't know, it's the base that we don't know. So we need to solve this equation. So we're going to go through those steps because it might not be immediately clear what you should do to remove that power of 8. So we're going to divide by 7,000 first because those two things are multiplied, so we can just divide off 7,000. Okay, always wait to round in these particular cases. So 15,000 divided by 7,000, we'll just simplify to 15 over 7, and that leaves us with a to the 8th. Now, we have a power that we need to undo. Remember what undoes powers? Roots. So what I'm going to do to both sides is take the 8th root of both sides, which is the same thing as taking both sides to the 1/8 power. And you can do that in your calculator. You can take a number to the 1/8 power. Just make sure you put parentheses if you're using that caret key around 1/8 and around 15/7. So you're going to need parentheses around both of those in your calculator. Okay, that undoes the 8th power here. If you do that in your calculator, you will get a long number. You will always get something, right? This isn't going to be a nice number, 15/7 to the 1/8 power. This is the growth factor though. It's incredibly important that you keep as many decimal places as possible. So I'm going to keep several here. When you do this math, you should get that A is about 1.0, and by this I mean keep 4 to 5 decimal places, or you're going to have a lot of error in your work. So I'm going to keep 5 decimal places there. You should get about 1.09995. If you cut that off too soon, remember this is the factor we're multiplying by with each increase of x. If we keep multiplying by a very rounded number, we're going to see a lot of error as we get further and further into our exponents. So keep a lot of decimal places there. We'll eventually talk about in this class too how we can just use this version of the number and do no rounding. But for right now, we'll go ahead and allow that rounding. We'll just want to keep a lot of decimal places. So your final answer here then is y equals 7,000, that original amount. Our growth factor is 1.09995. And that's what we'll take times 7,000 with each year that passes. Okay, so we'd be able to now find our investment amount after any number of years by plugging in an x. Okay. All right. So see if you can try this next one. See if you can figure it out before watching the video. Maybe pause and see if you can find that C and A, identify X and Y. I've given you some hints here in this problem for that. But we're going to go ahead and try this one out. So this time we're talking about populations. Populations are another thing that grow exponentially. In your presentation questions, I'll eventually bring that up with the population of people. Our population of humans has been growing exponentially as well. So here we're going to talk about a population of rabbits that has been tripling every year for 3 years. The population is now 44,000, and we want to construct an equation to describe the number of rabbits X years after it started tripling. Okay, so X we can clearly see is going to be years, and that means our output is going to be that our population is changing over those years. Again, we're growing exponentially because we're tripling. Just like exponential growth, we had exponential growth when that bacteria was doubling. Tripling right here, just that key word tells us that we are in fact growing exponentially. Okay, so we know we're going to be working with y equals c times a to the x, and we're trying to figure out, all right, do we know c? Do we know a? Do we know a combo of x and y to help us find any missing values for this equation? So I go back. I say, okay, it says a population has been tripling, and that means right there that my growth factor is 3. If I'm tripling, I'm multiplying by 3 every year. So we know A is 3 from tripling. Now, it's been doing this every year, so that's why we picked X to be the number of years, because with each year we will triple. It's been doing this for 3 years. We know the population right now is 44,000. So we don't know the initial population. We do not know C because we don't know what it was when it started tripling. We just know that after 3 years, an X value, our population is now 44,000. So this one will give you a good example of when you know A and another point, and you need to use that equation to find C to get your final equation. So we know Y is 44,000. We don't know C, but we know whatever C was, we took it times 3 times, because X is 3, to get to 44,000. And this is a little bit easier to solve for because we could take 3 cubed in our calculator and see that that is, oops, 3 cubed will end up being 27. And then we just need to divide both sides of this equation by 27. Again, it's important to keep, to not round as much here, but C is not what we multiply by over and over and over again. It's not our growth factor. We can be a little bit more lenient on our rounding with C. So I'm going to go with, since we're talking about populations, I'm going to round this to the nearest whole number, because that would make sense as a population, right? Having a whole rabbit to start with, okay? And that C value then is about 1,630 when you take 44,000 divided by 27. So you just want to put that all together now. Y equals that new initial population we figured out times A, which is still 3, but we're going to put that to the X power. All right, so that's our final equation, and then we can figure out, okay, what was the population after 1 year, after 2 years, those things that we don't know yet. Or if this continued to do it, right? We knew it happened for 3 years, but what if it continued for 4 years or 5 years or 6 years? We could then estimate the population after that. Okay, so we've really got to kind of dig into these and realize what pieces of information we know. I do want to make one point, especially with populations. So with populations, we can see that exponential growth, and we definitely do, but populations will eventually not be able to continue to grow exponentially. So populations, can they grow exponentially forever? The answer to that question is no. Can you think of why or why not they couldn't continue to grow exponentially forever? It's because eventually they'll run out of resources, right? Even our human population will eventually be too big for the planet, right? And that is something that we kind of worry about since we are seeing exponential growth in humans. And we've seen it in other populations as well. Anytime you start to have too much population, what happens is our population will start to level off. Basically something like kind of like what's happening right now, maybe a disease will start to wipe out some of the population. Now, I don't want that to freak you out at all. I think we've got a handle on what's going on in the world right now. But that is something that happens with deer populations, things like that. Before we were talking about that bacteria, right? Eventually it would run out of resources to grow on, and that population would start to level out. And we've been working on doing that to the human population for a long time. And that's what our presentation questions are going to explore. What are we doing to create that level off so that we don't just run out of resources, right? We don't run out of food, we don't run out of space, we don't run out of water, all the things that we need to survive. So we do often see exponential growth, but sometimes over time, we'll eventually see that level off happening. And for populations, that actually has a name. It's called the carrying capacity of whatever we're looking at. So that could happen with the bacteria or the rabbits that we were looking at, and so on. Okay, so populations cannot grow forever. Resources are limited. And so we'll eventually see them level off. All right. And we'll see that carrying capacity, which again, I mentioned, is just the maximum population available resources can support. Which I can't spell resources. Sorry about that. Also, sorry about my handwriting sometimes. I'm realizing like this max is not very legible at all. There we go. Sometimes I try and start to write too fast on the iPad. I can't keep up. Okay. So very good examples of creating those exponential functions. One big thing we like to talk about with exponential functions a lot is when we don't have a population that just doubles. All of them still have a doubling time, and we like to think about how fast that growth is happening and how much time it takes for something to double. So like at the very beginning, we looked at that bacteria population, and I talked about how it was changing in 20-minute time periods because it was easier to think about how long it took it to double rather than looking at that population every minute and then figuring out from there that it doubled every 20 minutes. So a lot of time we will talk about exponential growth in terms of doubling time. And if we aren't talking about it in terms of doubling time, we still want to be able to find that doubling time. We're going to do a couple different things with this example. We're going to look at how actually savings accounts, anything with an interest rate, so that includes your loans as well, grow exponentially when we're talking about interest. So we're going to first determine, okay, how is a savings account growing exponentially? And then we're going to use this example to find the savings account's doubling time. How long will it take our money to double in this account? A lot of the times, again, growth is quantified by that doubling time. So let's focus in on just the savings account example first. Interest is a percentage of the principal, or that starting amount of your account that is paid to the account holder. And the most simplified model, we just pay that same amount of interest every year. So that's what we're going to look at here. We're going to see how we can create an exponential model to calculate the savings account's balance after so many years if we invest $2,000 and earn an interest rate of 3.5% annually. So with the 0 years passing, we're going to put that $2,000 into our account, and that's going to be our balance. After 1 year, the way we calculate interest is to take that $2,000 and we would multiply it by the interest rate to figure out how much interest we earn. But one kind of trick here is to multiply by 1 plus the interest rate. And remember, percents, you always multiply by the percent in decimal form. So 3.5% is 0.035, okay? And we put that 1 in there so that we keep the $2,000 and then add in 3.5% of $2,000. So do this in your calculator. That's taking 2,000 times 1.035. And if you do that, you will get a number above 3,000. You will get the new balance of the account, which is $2,070 after the first year. Now, what happens with this is that a lot of savings accounts will then take the new balance. So we'll have the new balance here, which is $2,070. And again, we'll add that 1.035. We'll take it times 1.035 again to figure out what the new balance is, okay? But again, we want to relate this back to 2,000 if we can. So remember here, we got 2,070 from taking that original amount times 1.035 once. So then this becomes, okay, we took the original times the interest rate plus 1 once, and now we need to do it again. So we're going to take it times 1.035 again. That means we need to take 2,000 times 1.035 twice to get what happens after 2 years. Add in that interest rate twice. Now, notice it's not going to be 70 again because we're making more money on $2,070. 3.5% of that is higher than 3.5% of 2,000. So this is not a constant addition, it's a constant multiplication by 1 plus the interest rate. And here we will get $2,142.45 is the balance after 2 years. So if you can see that trend now, then after 3 years, we'll take that $2,000 and take it times 1.035 how many times? 3 times. And we'll end up there with $2,217 and rounding to the nearest cent, 44 cents. So bank accounts, because they're in terms of percentages, interest rates, and we have to take percentages times the original amount to get the new amount. We're doing that repeated multiplication, and we find out that we have exponential growth because the savings account will equal that original that initial investment times 1 plus our interest rate, and we'll multiply for however many years we're looking at. And that is an equation of exponential growth. All right, so you'll have practice with that too in your homework, setting up those equations with savings account balances. Now, sometimes it's kind of hard to understand, okay, what is a 3.5% interest rate versus a 4.5% interest rate? And again, quantifying that growth instead in terms of the doubling time of this account is very helpful. So we're going to look for, okay, how long would it take for this savings account to double? How long would it take for S to become about 4,000, right? For that $2,000 to double. So we're going to test some values, all right? So we know we start off at 2,000 if N is 0. So I'm going to jump, I'm going to make an educated guess, 3.5%. I can see that after 3 years, I've only gained about $200. So I'm going to jump up to 10 and see what I get after 10 years by using my equation. So that would be plugging it into my calculator, 2,000 times 1.035 to the 10th power. And after 10 years, I'll see that my account will be worth $2,821.20. Okay, so not close to 4,000 yet. So I'm going to jump up another 10. Okay, we need to go pretty far. But we know this growth happens fast, so we don't want to jump too far too fast. Okay, so we'll take that now in our calculator to the 20th power. And then we'll see that that gets to be 3,700 and, sorry, just reversed 2 numbers there. $3,979.58, and that's pretty close to 4,000 there. So what we're seeing is that after 20 years, we just about double our money. Even if you go to 21, you'll be a little bit past 4,000 there. So I'm going to say my doubling time then is about 20 years, because after 20 years, I get very close to that doubling of my money at 4,000. Whoa, goodness, doubling, I just put ing twice. Okay. Doubling time we're seeing there is about 20 years. So for me, just do a couple more, plug in 30, this will be just good practice with your calculator, and 40, and see what you get for those. So we wouldn't normally continue to go because we have the doubling time, but I want to show you what happens after yet another 20 years. So after 30 years, just for good practice, you should have gotten about $5,613.59. Just again, showing you how that exponential growth really helps, right? Our money is growing faster and faster. Okay, but in terms of doubling time, that stays constant. So our money grows faster and faster, right? But our doubling time stays the same because our money is growing faster. I only gained $2,000 to get from 2,000 to 4,000, but I'll gain $4,000 to double again to get to 8,000, about, right? Very close. So we still have a doubling time that stays constant because every time we double, we gain more money, right? Here we only gained 2,000, whereas in the next doubling time, I double from 4,000, so I gain 4,000. I gain double as much. Okay, so doubling time is a really good way to quantify that exponential growth. So here, your estimate, and it's just an estimate, right? We know that that's not exactly 8,000, but it's pretty close. It's around 20 years for the doubling time of this savings account balance. Okay, so right now, again, we're just doing some good educated guessing in order to get those output values that we're looking for. All right, try the homework and email me with questions. And I still have those help hours on Friday during our normal class time if you need it. And always email me. I'm more than happy to help you through there too.